Hello everyone, let us take one more example of simply supported beam with uniformly varying load. This is another case, second case we are taking, and different type of loading is there in this case, right? Previously the loading was there and it was maximum at one end and zero at the other end. Now we are taking the different case where there is the zero loading at endpoints and maximum loading at the center. At the center there is maximum loading and zero loading at the endpoints like this, right? So this is the UVL, uniformly varying load. In downward direction this is the load like this, right? So it is maximum at the center and zero loading at the end. And what is this loading at the center? At the center this is W kilonewton per meter. So it is changing from W kilonewton to zero from center to the endpoints, right? And we want to find out, we want to draw the shear force and bending moment diagram for this case. Shear force and bending moment diagram for this case, right? We want to draw this, right? And suppose the length of this beam is L. It is given to us, length is given to us, also loading is given to us, W kilonewton per meter, and this is maximum at the center. And we want to draw the shear force bending moment diagram. First of all, we want to find out the reaction. What will be the reaction at point A and the reaction at point B? This is our point, right? RA and RB, and we want to find out the reactions at point A and B. What will be the loading? What will be the total loading? You can see here there are two triangles basically, symmetrical triangles. Symmetry is there, center is maximum and then it is reducing, so symmetry is there. So what will be the loading of one triangle? This will be half multiplied by height, which is W, multiplied by the base, which is L by 2. So this is WL by 2. So for this triangle, so this is leftward triangle, the total load will be at this point, which is WL by 2, and for this triangle again the total load will be acting at this point, and again it will be half multiplied by base multiplied by height. So this will be WL by 4 because the length is L by 2 for this. So this length is L by 2. You can see here this is half, right? So this is WL 4, and again here it is WL by 4. So you can see here there are two triangles here, symmetrical triangles are there, and one triangle have a load of WL by 4 and concentrated at the center of gravity of this triangle. Another load is again WL by 4 concentrated at the center of gravity of this triangle, right? We can see here this is suppose G1 and this is suppose G2. But because there is symmetry, we can think of that total load of this system will be acting at the center of this beam, right? Because there is symmetry from here and here. So rather than doing this and this, we can use this concept that there is symmetry and total load. And what will be the total load? That will be WL by 4 plus WL by 4. So this will be WL by 2 at this point center. So at center, total load acting is WL by 2. So we will omit these forces now. This force we will not use in our calculation. This force we will not use in our calculation because we have omitted these into a single force acting at the center due to symmetry, which is at a length of L by 2 from the point A. So no need to use WL by 4 and WL by 4 because we are replacing this WL by 4 and WL by 4 with a single load of WL by 2 acting at the center, right? So finding the reaction RA and RB. So take moment about any hinge point or roller point and find out the sum of the moments, and you can find out and that sum of the moment at a point A will be equal to 0. So take moment about point A. Take moment about point A, and you know that sum of the moments about point A should be equal to 0, right? So what can we do now? We can take the moment. So we have, how many forces are there? There are only three forces: RA, WL by 2 and RB. RA, WL by 2 and RB, right? So these are the forces. So RA, the moment of RA about A will be equal to 0 because it is passing through A itself and there is no perpendicular distance between A and RA. So the moment of RA will be equal to 0. Moment of WL by 2, this is clockwise, let us take clockwise positive, WL by 2 multiplied by the length, it is L by 2. This distance is L by 2. So WL by 2 has a moment of WL by 2 multiplied L by 2, and we are taking it positive, clockwise positive and anti-clockwise negative. So RB multiplied by L. So minus RB multiplied by L, and that should be equal to 0. So from here we can find out the reaction RB. L will cancel out, you will get WL by 4. So RB will be equal to WL by 4, right? So this is one of the reaction. Another reaction can be find out using the sum of forces in vertical direction equal to 0, this statical equilibrium condition, and sum of the forces in vertical direction equal to 0. There are three forces. RA, RB and WL by 2, right? This we have omitted because these two combine together to into a one single force WL by 2, right? So downward force is WL by 2, we are taking downward force as positive, minus RA minus RB, and RB we have already found out, WL by 4. Solve it and you will get RA, and that will be equal to, RA will come out to be WL by 4 again, and you can see there is symmetry that WL by 2 is in downward direction at the center, so these should be equal, RA and RB, and half WL by 4, right? So RA is WL by 4, RA is WL by 4. Similarly RB is also equal to WL by 4. So this is the case with reactions at point A and B. Now we want to find out the shear force diagram and bending moment diagram. For this, that we have to take any point, suppose at left or right of the section, and find out the shear force on that point. So let us take any point here, suppose x dash we have taken, and at a distance x from B, let us take this, right? So we have taken at a distance x, a distance x dash, and we want to find out what is happening here in this triangle. So what is the shear force at this point, and this will be valid from B to C. It will be valid from B to C, right? And there is symmetry here, right? So similarly we can take a section here also. First of all, we are taking section here from B at a distance x. So what is happening in this triangle? Let us make this triangle here. We want to make this triangle here. This is the triangle. This triangle. I have made somewhat bigger so that clarity is there. BX dash is there. This triangle, and there will be a force acting at the centroid of this triangle, and this distance is x. And what will be the force here? That will be the area of this triangle. Half multiplied by base multiplied by height. But what is this x dash? Height. If this is W at a length of L by 2, then it will be at a distance x, what will be the value? So W at a length of L by 2, what is the distance at distance x? So this is 2wx by L. So this is the length, 2wx by L. So this is 2wx by L. In a length of L by 2, the total load is W. At a distance of x, what will be the load? So this is this, and this distance is x, and the force acting downward will be the equal to the area of this triangle, and area of this triangle is half multiplied by base multiplied by height. So this will be Wx square by L. Wx square by L. So this much force will be acting. This much force will be acting in the downward direction at a distance of, and what is this distance? This distance will be x by 3. X by 3. At a distance of x by 3 from this x dash, right? So this is distance is x by 3 and the load is Wx square by L. This load is acting in downward direction equal to the area of this triangle. So this is happening here, and RB is upward. So here RB is upward. We are making RB here itself. This is RB. So we have made that triangle here, and there are two forces acting to the right of this cross section. One is RB upward and one is Wx square by L downward. So we have two forces basically, right? So if you want to find out shear force at a distance x, shear force at this section, what is the definition? Sum of all the forces, all the vertical forces to the right of the section, right? Sum of all the forces to the right of the section. So to the right of section there are two forces, RB upward, Wx square by L downward. So downward force on the right section is positive and upward force on the right section is negative. So we can write Wx square by L positive minus RB upward. RB is WL by 4. And this is valid from B to C. This is valid from B to C. So this is the shear force which is valid from B to C, isn't it? And this is a parabolic variation. Now we can find out the shear force at the peak points, like at B and C, at endpoints B and C. So what will be the shear force at point B? At point B, x will be 0. At point B, x will be 0. So put x equal to 0 here, and you will get minus WL by 4. This is the shear force at x is equal to 0. Shear force at x is equal to 0. Another is minus WL by 4 at x is equal to 0. So another is, what is the value at point C? At point C, what is the value? At C point, x is L by 2. X will be L by 2. So put here x L by 2. So you will get L by 2, it will become 4, this will become 0. So FC you will get equal to 0 at x equal to L by 2. So this is the shear force at point B and point C, right? And it is valid between B to C. At B the value is minus WL by 4 and at C the value is 0, and we are getting a parabolic variation, right? Now this we have taken on this side, on the right of this part from B to C. But what is happening from A to C, in part A to C? For that, what we can do is we can take another section. We can take another section at this point. Here from A you can take one more cross section, suppose x dash, at a distance x. And this triangle is very similar to this triangle. This triangle is very similar to this triangle. You can see here we are talking about this triangle, AX dash, right? So what is happening here, and using this we can find out the shear force between A to C, right? So what is happening in this part? So I am making here this triangle. This triangle I have made. This is point A. This is x dash, right? And this is the triangle we are talking about, this triangle between the part AC, right? And the centroid will be acting at this point, and this perpendicular distance will be 2wx by L, because both are same. 2wx by L, 2wx by L, and the load will be wx square by L, wx square by L. Both are very similar, and distance is x, and this distance will be x by 3. This distance will be x by 3, right? And load will be same, wx square by L, and this distance x by 3, this distance is x by 3. And the length of this ax is a capital X, small x. Length of this is small x, like this. So this is the way we can find out the shear force in part AC using this condition, right? Because this triangle is a part of AC. So for AC, we can take another part like this, Fx, again Fx for part AC. All the stresses, all the forces to the left of the section, right? This is point A, and here this reaction is RA. So there are two forces to the left of the section. One is RA, one is wx square by L. RA is leftward upward, which is positive, and wx square by L is left downward, which is negative, right? So this is positive RA, this is negative. So RA is WL by 4. So we can write positive WL by 4, which was negative here, and minus wx square by L. And this is valid between A to C. Then what is FA? When x is equal to 0, this is WL by 4. And what is FC? FC will be 0. Put here x is equal to L by 2. Here x is equal to 0. Here we have put x is equal to L by 2. So we have find out FB, FA and FC. And the variation is parabolic for both cases. Now we can draw shear force diagram. So shear force diagram can be drawn based on this information. So let us have a straight line, and at this point the length is this much, WL by 4. This is the shear force at point A. Shear force at point A. At point B, shear force is minus WL by 4. So at point B, the shear force is minus WL by 4. At point C, shear force is 0. This is our center, shear force is 0. And the variation is parabolic. Parabolic variation is there, right? So parabolic variation will be like this. One curve for this and another curve for this. So this type of curve we will be getting. This is the curve which will be obtained for this case, right? And this is positive and this is negative. And this variation is parabolic, and at point C the shear force is 0. You know that the point of shear force will be the maximum bending moment point also, right? So here maximum bending moment will be obtained when we find out the maximum bending moment. So this is the shear force diagram. Shear force diagram. That at endpoints A and B, the shear force is WL by 4 positive, here WL by 4 negative, and the curve is parabolic. You can see here, this is parabola. You can see here, this is again parabola, this type of parabola, right? So parabolic curve is there, and at endpoints the shear force is WL by 4. So this is the shear force diagram. Next we want to find out the bending moment diagram. How to draw the bending moment diagram? For that we have to find out the bending moment at point X while taking from B side, and at point X while taking from A side, similar to the shear force diagram. So bending moment diagram, finding the MX from B side, we are taking from B side, this part, B side, right? So what are the forces to the right of the section? There are two forces, RB and WX square by L. RB is at a distance x, WX square by L is at a distance x by 3. Take the moment of these two forces about x. Take the moment of these forces about x, and that will be the bending moment at x, right? So RB will be positive, the moment of RB will be positive because it is anti-clockwise to the right, and it is clockwise to the right of the section, this is negative according to our sign convention. So RB multiplied by X, and what is RB? WL by 4. So WLX by 4. Moment of RB about X. So this is moment of this, right? And this is minus because it is clockwise. Wx square by L multiplied by X by 3. So this will become Wx cube by 3L. Wx cube by 3L, right? So WLX by 4 minus Wx cube by 3L. This is the bending moment, right? And this is valid from B to C. Valid from B to C. B to C. Is it okay? So what is bending moment at B? At B, the X is 0. So X is 0. Put here 0, you will get 0. So where X is equal to 0. And what is bending moment at C? And that will be equal to, at C point shear force is 0, it should come maximum bending moment. So it will come maximum bending moment. At C point is at distance L by 2. So at L by 2, put here L by 2, L by 2, you will get, put value of, here put X is equal to L by 2, you will get the bending moment at point C, and put it and you will get the value as WL square by 12. WL square by 12. Solve it and you will get, put X is equal to L by 2, X is equal to L by 2, and solve it and you will get this thing. And this is at X is equal to L by 2 at the center, right? And it is maximum because shear force is 0 at this point. Now this is the bending moment diagram from 0 to this value, positive value on right side from B to C. This is valid from B to C. Now from A to B, A to C, again find out bending moment for this case, right? We have taken the section, take the section and find out the moment of the forces to the left of the section. And to the left of the section there are two forces, RA and Wx square by L. Moment of RA, and that should be positive, leftward clockwise positive, leftward anti-clockwise, for this it is negative. So RA multiplied by X. So RA multiplied by X, X is WL by 4 into X. Same will come WLX by 4 minus WX cube by 3L, and now it is valid from A to C. And MA will be equal to 0, put X is equal to 0 here, and MC will be equal to, same value will come out, WL square by 12, where X is equal to L by 2, right? So this is a cubic parabola. So what type of curve you will get? The curve you will get a cubic parabola like this. Suppose this is our beam from A to B, and this is center point C. At C point there will be maximum bending moment. At C point the bending moment will be maximum, and it is a curvature cubic parabola from WL square by 12. So this value will be WL square by 12, suppose this value, and it is from 0 to WL square by 12, and then WL square by 12 to 0. So this type of curve you will get, and this height, which is the maximum bending moment, Mmax, this is WL square by 12, right? So this is how the maximum bending moment and the shear force and bending moment diagram is obtained. This is bending moment diagram. Upward shear force diagram. This is the bending moment diagram for simply supported beam when the UVL is loaded in this manner.